Now, what is the need for data conversion? We have already an SMDP, IEP on A to D and D to A converter, so they must be important in some way, right? So what happens is that today, for the ease of storage and processing, you always have a digital signal processing core in any system. So this block diagram shows a generic signal processing system of today. It could be anything. It could be your audio player. It could be your radio. Anything. Most of them look like this. Okay. But any system also has to interface with real world signals. It has to take in signals. For instance, here shows a microphone. It has to take in the audio. And here is the antenna. It may have to take in some radio signal. And it may have to output audio. It may have to output an RF signal like your cell phone. But in the core of the cell phone or the audio player, there will be DSP. Okay. So we have to go between these signals, real world signals, which are continuous time signals and have a continuous values of amplitude, to the digital signal processing core, which is sampled and also has discrete amplitude levels. Okay. And finally, it also has to go the other way. It has to convert these discrete time, discrete amplitude levels to continuous time, continuous amplitude signals. And the part that takes in the signal and converts it to digital, that is known as an analog to digital converter. And the one that goes the other way around, from digital to analog, is obviously a digital to analog converter. Okay. So what we'll see is some styles of making these A to D converters, and perhaps if we have time, some D to A converters. So this is what I said just now. For interfacing between the real world and the DSP core, we need the data conversion circuits. And there is a wide variety of precision and speed. I mean, it's not that every A to D converter is the same thing. The one that you need for audio operates very slowly, but has very high precision. The one that you use for maybe some high-speed signal in an oscilloscope has a very high speed, but a much lower precision. Okay. So similarly for D to A converters, there is a huge variety, but there are some general underlying principles which we have to understand that we'll go through in the beginning. So this slide shows a generic continuous time signal. The x-axis is time. I've just marked some intervals TS, 2TS and so on. That's just graduation marks on the time axis. And as you can see, it is defined for all values of time. And also along the y-axis, any possible value, any value is possible. Okay. So you can have it 0.1 VLSI or 0.01 or 0.35210, whatever it is. Okay. So this signal which is defined for all time in continuous time sense, and also it can take on any amplitude along the amplitude axis, is known as a continuous time signal. Okay, this is the most familiar analog signal. Now we have another type of signal, which is a discrete time signal. In this case, the signals can take on any value, but it is defined only for the sampling instants. Okay, here I have marked them 0, 1, 2, 3 and so on. So there is nothing between 0 and 1. It's not as though the signal is 0 between 0 and 1. It's simply not defined. Okay, it's defined only for 0, next for 1, next for 2 and so on. So this is a discrete time signal. And this is another type of signal which is defined for discrete instants of time. Not only that, it cannot take on any values. As you see, it can take either 0 or VLSI or 2 VLSI and so on. Okay. So these are known as digital signals. A special case of this is something that can take only two values, and that's the binary digital signal. That's what most of us think of as a digital signal. But this is also a digital signal, as long as it is quantized on the y-axis. Okay. Just a moment. Let me. Okay. So if you take a short segment of continuous time signal, let's say my speaking this one sentence, if you take that signal, it has infinite number of points even in that finite segment, and also each value is defined with infinite precision, okay, because it can take on any value. Now, when we discretize the time, that is we sample the signal only at some instance of time, we get only a finite number of samples, but the value itself is still defined with infinite precision, okay. And then you quantize the amplitude also, that is you let it take on only some amplitude values. Then what happens is if you take a finite segment, let's say my speaking this sentence, you will end up with a finite number of points. That's why it is convenient for storage, okay. It's very hard to store a continuous time signal because there are an infinite number of points. Whereas here, if you sample it along the time axis and also quantize it along the y-axis, if you take this length of speech, you will have a finite number of points. That's the main reason why we do that. And this whole process of sampling and quantization, that is you first look at it only at some instance of time, and then you also let it take only some discrete values, that is known as analog to digital conversion, okay. That's a combination of sampling and quantization, okay. Now the question is, original signal was continuous time, continuous amplitude, and we have come up with something that is discrete time and discrete amplitude. So we have a totally different signal. Are there errors in the process? Okay, because obviously if the signal that we get has no relationship to what we started off with, it's completely useless. Why would we want to do that? So we want to see if there are some errors. Now intuitively also we feel it is okay, because if we go on making the sampling instant finer and finer, and the amplitude values also finer and finer, we get the original signal. So we feel that this is okay, but we have to see how much we have to quantize it, how often we have to sample it. Okay, so that we'll proceed to do now. So for this we need to have some knowledge of Fourier transforms, okay, because these things are best analyzed in the frequency domain. So let's say we have a continuous time signal XCT, then its frequency domain representation is XCT of f, which is given by this formula. Like all of you are familiar with the Fourier transforms and use it regularly. Okay. And then let's say we have a discrete time signal XD, which is defined for some index n. Okay, the x-axis is not t but some numbers n. Then it also has a frequency domain representation. This new frequency I call nu, the Greek letter nu, and that is because here t is continuous and here n is discrete. Here I have an integral and here I have a summation. Okay. So it's not our objective to go into detailed analysis of the transforms themselves, but to use them. So this is just a refresher of the definition. Okay. So as long as you know these definitions and know some manipulations, you can figure out what happens to signals when you sample them. Okay. And finally, one thing to note is that the Fourier transform of a discrete time signal is periodic with 1. Okay. So XT looks like something from 0 to 1, and after that it keeps repeating. Okay. Periodic XD, the Fourier transform of the discrete time signal. I'll show pictures of this also. So here on the left side I have shown some continuous time signal. Okay. This is a continuous amplitude signal. And on the right side I have shown the Fourier transform of that one, the magnitude of the Fourier transform. Okay. And it has some shape. The exact shape need not worry, as I have taken some signal as an example. So it starts from here and goes to this point FB, which I have labeled FB, and then after that it is almost 0. So this FB is something I call the signal bandwidth. Okay. Now every signal, depending on how it varies, has some bandwidth. It's just important for us to know that there is something that's called the signal bandwidth. Basically, that is the point beyond which the signal has insignificant energy. Okay. So this is how the continuous time signal looks like in the time and frequency domains. Now I sample it. Okay, I have taken, you can see that it's the shape of this is the same as the shape of this one. So, okay, I have taken the values only at some instance and I have made it a discrete time signal. So what happens? You get the exact same shape as before, but then it goes on repeating. Everyone is familiar with this phenomenon? What is it called? Huh? What happens when you sample a signal in the frequency domain? You get a periodic spectrum, you get copies, and there is possibility of aliasing, right? That's what it is called. So, this is periodic with period of 1. That's what I meant earlier. So, the Fourier transform goes on repeating. Okay? Now, if you start with a real signal, that is signal which has only real values, we only need to look at the Fourier transform between 0 and 0.5. Okay? This is again something that's a property of the Fourier transform, you know that. So, we don't have to look everywhere, and clearly we don't have to look beyond 1, because whatever is between 0 and 1 is exactly the same thing between 1 and 2 and so on. So, we have to look at only this segment, and for real signals we have to look at only between 0 and half. Okay. So, now let us go to our sampling process. So, those were just examples of what Fourier transforms of continuous time and discrete time signals look like. Okay. The continuous time signal typically has some bandwidth beyond which it has no energy, and a discrete time signal is periodic. I mean, it has a periodic Fourier transform. Okay. Now, let us say I have the continuous time signal that is denoted by the dashed line here. Okay. And that I sample to get these samples 0, 1, 2, 3. Okay. I sample it at TS, 2TS, 3TS to get these dots, the samples. So, that is denoted in the time domain like this. Now, what will I get in the frequency domain if I do this? Yeah. So, that's true, it is periodic, but what will be the shape of the spectrum? Same. Okay. So, we start with a continuous time signal, it has some spectrum, and then we sample it. What happens is, this black stuff is the continuous time spectrum, and then that goes on repeating. Whatever we start off with is what goes on repeating. Okay. So, that's what is given by this expression. Right. So, there will be copies of signal spectrum at Fs if you look at the frequency axis. Now also, the other thing, again, something that you must be familiar with, that you start with something like this, and then you start with something like this, and then it repeats. Right? Where does it repeat? It has copies at every Fs. Okay. So, if Fs is very small, what happens? Yeah. So, some portion of this copy and some portion of the next copy will fall on top of each other. Okay. That is what is called as aliasing. Okay. Now, if there is no aliasing, let's say you have this and the next copy comes after this has gone to 0, then you can easily see that you can reconstruct the signal. Okay. You can simply you can look at only the first part of it and reconstruct the signal. But if some portion has got alias, then you will not be able to do that. Okay. So, this is an example of sampling without aliasing. The black stuff is the spectrum of the continuous time signal, and the red stuff is simply the same thing which has been copied. Okay. And to get back the original signal, what do? I just have a filter which will take out only the first part. Okay. How we implement the filter is not relevant here, but this is what we do. Okay. Now, in this case, I have chosen my Fs to be here, right? Sorry, it's actually there is a mistake here. Fs is here. So, what happens is there is one copy like this and another copy like this, which have got added together. Okay. This is the bandwidth. Now, in the first case, my FS was here. Okay. So I get one copy of this, and remember that all of these things are symmetric. Okay. So the whole thing gets copied over again. So one copy is not interfering with another copy. And the next time around, let's say I choose my FS to be here. So I get one copy, which is exactly like before, and my second copy will appear here, and my third copy will appear here, and so on. So what will happen? The net sum will be something like that. Okay. So can we get back the original from this? How will we do that? We can't do anything because we have just added up, folded for some parts of the spectrum. Whereas in the second case, we could do this and get it out. There's nothing we can do to the third one to get it out. Okay. So what is the point of all this analysis? Yeah. See, we already said that we want to sample because we want to have a finite number of points. But you can't take one sample today, another sample tomorrow, and expect to reconstruct my whole lecture, right? This is exactly like you walk into a lecture now, maybe 1 hour later, 2 hours later, you won't be able to figure out what's happening. But even if you go to sleep once in a while, it's okay. As long as you wake up every now and then, maybe you'll be able to reconstruct the lecture. You have to sample often enough, right? If you sleep the whole time, clearly you won't be able to reconstruct the lecture. Okay? So I'm not asking you to apply this in this lecture, but yeah, that's an idea, right? If you do feel sleepy, at least make sure that you wake up every now and then. Okay? So we want to sample, but then there are some constraints. So this puts a limit on FS. What does it mean? That means that you have to sample with a certain frequency or higher. You can't go on sampling, you can't go on taking fewer and fewer samples. Okay? So this is one part of the game. We wanted to sample. The next thing is quantization. What will happen with quantization? Yeah? No. See. That's correct. Yeah. No, there are two separate things. The one is the statistical part and the other is time limited thing. Okay. Let's say we have a time limited signal. It is surely not exactly band limited. Okay. Now the idea also is generally you neglect things that are very small. Right. That's a practical thing that we always do. You can't go on taking things to infinity even if it's very small. That is mathematics. As engineers, when you're accounting, you maybe account for the expense of your car and everything, but if you go and have tea on the roadside, probably you won't write it in your account book, right? Similarly, if the signal strength is below some value, so let's say, as you say, it will never go to 0. Okay? So let's say here it is 1. And here it is 10 to the minus 6. And after that it goes to below 10 to the minus 6. Now, you decide that you will neglect everything below 10 to the minus 6. So that's how, in practice, every signal is band limited. Okay? Although in reality it will never go to 0, you have to choose some point below which it is negligible. Now, what is negligible also depends on the application. In some cases it may be 10 to the minus 6, in some cases it may be 10 to the minus 2. Okay? So, we have different measures of bandwidth. Now, what does this negligible really mean? One way to figure it out empirically. Let's say you don't do any theory because it's a little bit hard to do. So you first put a filter to this part and then play it back and see. If it sounds the same, then you say that is okay, right? That is one way to look at it. So you decide something is negligible. So for instance, for human audio, it's been decided that obviously maybe we may be emitting some sounds beyond 20 kilohertz also, but if we take from 0 to 24 kilohertz, that's it. We don't need anything more, okay? Because our ears don't respond to it, and we can't produce those sounds either. So that's what has been decided. Okay. Although if you take a finite segment of my speech, it is strictly not band limited at all, right? So there are some practical definitions like that. Now the second part is statistical. That is a different thing. That is because, like every time I'm speaking, I'm not producing exactly the same sounds. Even if I say the same sentence, some things will be different. So the spectral density and so on is some kind of an average of my speech, like many samples of my speech, over and over. So that statistical thing you need to get, because first of all you have different things every time. Okay. I mean, that's the nature of information. If I was going to say the same thing now and the next sentence is the same thing, there is no motivation for you to sit here, right? So it's only because I'm saying different things. Now to describe it in the frequency domain, I'll need some statistics. Okay. But yeah, in practice you identify some point beyond which the energy is very small. Okay. So from this we get an idea. Bandwidth, while ideally it means the energy is 0, in practice it means energy is very small. So you have to sample at some rate in relation to the bandwidth, and that relationship I'm sure everybody knows. The sampling rate should be at least 2 times the bandwidth. And this picture we can get very easily from the frequency domain. That's why we go to the frequency domain, because by looking at the time domain signal I couldn't tell. Okay. If I have a signal like this, should I be sampling like this or should I be sampling finer? It's hard to tell, but in the frequency domain it's very easy. That's why we go to the frequency domain. Okay. So this is one half of the game. Now we know we can sample, but we have to sample at a certain rate at least. Now the next part is quantization. What do you think will happen with quantization? Will there be errors? Will there be errors? Surely there will be errors, because if the input is 0.0013, I'll probably round it off to 0.01 or something. Okay. So I am rounding off basically. Again there will be errors. So but how much error is there? What kind of error is it? Yeah, that may be so. But first of all, is it okay to quantize? No, okay, let's say no option. There may be no options to do many things, but there may be no way to do it also, right? Is it okay? I mean, intuitively, do you feel quantizing is okay? So again, see, there are many things that are not significant which you can leave out, right? When you are doing accounting, you probably won't write the paise. That is quantization, right? You ignore the paise and round it off to the next rupee, that is quantization. Now, if you are doing some mental calculation for a house, you won't quantize it even to the nearest rupee. You will probably do it to the nearest 1,000 rupees. Okay, so your quantization is even cruder. And that's also okay, because when you are spending like maybe 25 lakhs to build a house, some 25 paise here and there is not going to matter, right? So how much error should be there? How do we decide? Depends on the situation and my rounding increment, right? What is the maximum error I will make? If I round it off to the nearest rupee, what is the maximum error I will be making? No. I mean, what is the maximum? 50 paise, right? I mean, if I am rounding off every expense to the nearest rupee, the maximum error I will make is 50 paise. That may be okay. And then if you are rounding off to the nearest 1,000, then the maximum error is 500 rupees, and that may also be okay in some other situation. Okay, and if you are dealing with crores of bribes, maybe like 50 lakhs is also okay here and there. No. I think you always go for uniform quantization. The question is how much error you will make, and that you have to limit. And like somebody pointed out, it depends on the situation, how much error that is there. But if the rounding is 1 rupee, the error is 50 paise. That is very clear, right? Similarly, if the rounding is some VLSI volts, the maximum error we will make will be VLSB by 2. We will see what the effect of that is soon. This is what happens. So the black ones are what I got by sampling. Next, what I have done is, the y-axis I have graduated in intervals of VLSB, which is my 1 rupee. Okay. And I look at the black sample and I round it off to the nearest graduation mark. Okay, that you can clearly see here. So there is a large error here, relatively small error here. My first sample was 0, so there is no error. So the error can be anywhere between 0 and half of VLSB. Okay. So that's what happens with quantization. Now, exactly the quantization error itself depends on the signal. Okay. Now, this is where statistics comes in, because you don't want to look at every signal and calculate every sample and calculate the quantization error from there. We want to be able to tell something about the quantization error without looking into the details of the signal. So, we use statistics. So, that means, first of all, we already know one thing, that the error will not be more than VLSB by 2. Okay, if we do the rounding correctly. Okay. So, we will come back to the statistics soon. Now, here what I did was I first sampled and then I quantized. Okay. In case of sampling, I had these Fourier transforms and I was able to tell you what the Fourier transform of the sampled signal looks like. It is simply copies. What will be the Fourier transform of the quantized signal? Is there some easy way to tell? What do you think it will be? After you quantize it. Quantization is non-linear, like somebody already said. Okay. Because if you add two inputs and apply to it, the output is not really the sum of individual outputs. Superposition doesn't apply. So it is definitely non-linear. But how would you find out the spectrum of the quantized signal? See, this is what we want to do. We have different ways of describing the signal. One is in time domain, another is in frequency domain. So sometimes one is easier than the other. Now we have gone through sampling. It's easier to see what happens in the frequency domain. Then we go through quantization also. Again, we want to see what happens in the frequency domain, just to get a clear picture. How? Why will there be a sync? No, that's okay. See, I already know what happens to the sample signal. When I go from sample to quantization, what will happen to that? Huh? How? Okay, you're saying noise floor added. How do we know that noise floor is added and how much noise floor is added? Which one? But what is the quantization error? That's what we want to find out, right? No, that's okay. But what I'm trying to get at is, see, this is the spectrum of the sample signal. Now I have quantization also, and you are saying there is error. But what kind of error will it be? I mean, it could be an error like this, it could be an error like this, it could be an error like this, or in some other shape. I don't know. How would I find out? In the frequency domain, I want to see. Okay. And how will I do it? No, it will surely be repeated because it is also sampled. But there will be some errors beyond the signal, right? What kind of errors will that be? No, but yeah, why do we assume it's white? It is certainly correlated with signal, right? Because for every sample there is a certain quantization error. It is very much correlated with the signal. Why do we get that white-like spectrum? Yeah, that's true. The result you are getting at is right. But how do we even get it? Because we know that it is certainly correlated with the signal. Okay? Because if I round off 75 paise to 1 rupee, I know that the error is 25 paise. There is no other thing. Okay? Or in general, let's say, how do we find out the spectrum of a quantized signal? Okay, what really happens when you quantize it? Now, so it is a little bit of a hard thing. You first sample and then quantize. It's generally not easy to figure out what happens. Okay. In this case, what I've done is, I've taken the continuous time signal, I've first quantized it. Okay. That is, at every point I look at, this is some theoretical thing I do. I don't have to be able to implement this. But at every point I round it off to the nearest VLSI. So I get this black signal. Okay. Is that okay? I've taken the continuous time signal and at every point I've rounded it off to the nearest VLSI. And after that I sample it. Okay. Is it exactly the same as sampling followed by quantization? If I interchange the two? I first quantize and then sample, or I first sample and then quantize. Will it be exactly the same? Why not? Will I be getting the same points or no? Points we will get the same. So it is exactly the same. Right? If we get exactly the same output, it is the same system. We won't be able to tell. Right? If I gave you a black box with a sampler followed by a quantizer, or a quantizer followed by a sampler, you won't be able to tell. Right? Is it okay or no? If it's not, it's not okay. Yeah. Yeah. No, that is okay. This is what we are trying to do is to find out how much the error is. Okay. All I'm saying is, if let's say I want to look at the sample at 2Ts. Okay. So here, I first sample it, I get something, this looks like slightly more than half of VLSI, and then I round it off to VLSI. Okay. Here, in this whole region, it is rounded off to VLSI, and then I sample it. Will I get the same value or no? You have to, right? Okay. Is it okay or no? So let's say you take your daily expenses again, and then you sample like the expense for the first of every month, and then you round it off to 1 rupee. Or every day you round it off, and then I take it for the first of every month. The result will be exactly the same. Okay. Now, what is the use of this? Why would this is like mathematical operations, right? Sometimes to do analysis, you first do integration and then summation, or summation and then integration, things like that. What is the advantage of this thing? Or at least from this process, let's say now I have already established that doing quantization first and then sampling afterwards is exactly the same as sampling first and quantization afterwards. How will this help in my analysis? What happens if I do quantization first in the frequency domain? No, I think you are confusing. The sink refers to the Fourier transform of a pulse, okay, of some width. Now here the width is something that depends on the signal. Okay, it is a nonlinear process, right? I have a sine wave, I pass it through a quantizer. What will the spectrum look like? I have a sine wave, I pass it through a quantizer, and the output will certainly have the steps, something like this. It will have the steps, it will go up and down. What? Yeah, so what is the spectrum? What will it look like? No, but it's not always half LSB, right? Is it noise? What will it look like? Let's see what. This is not sampled, mind you. I am only passing it through a quantizer. Okay. I have a sine wave. Okay. First, maybe let's go to the first step. What will be the spectrum of this? Yeah. Okay. So let's take only one half. So it's an impulse. Okay. Whatever frequency it is. It's an impulse. So this is F, this is T. Okay, and then I round it off to some levels. Okay, so something like this. Let's say I'm not showing this correctly perhaps, but okay, something like that. So it is stepped, and it will keep on going, just the same way that the sine wave keeps repeating. This will keep on going. What will the spectrum of this look like?
So it is actually a sine wave followed by half LSB between rectangular ray of
okay, but that's fine. That's absolutely right. Clearly, you are decomposing it into sine wave and another one. But what will the spectrum look like? That's fine. But what is the shape of the spectrum? I mean, what will I see in the frequency domain? That's not true. No, there is no sampling here. That's what I'm saying. I have just quantized. At every point, I have rounded it off. Okay, what will the spectrum of this look like? No, okay, the shape, what will I see? See, clearly all of you said, the moment I put the sine wave, you said I'll see an impulse on the frequency axis, right? What will I see in this case? How will that come about? Let's take a simpler case. I have this, okay, and clearly again I have this impulse. Now I'll quantize it only into two levels. Okay, I'm really crude. Let's say if I owe you money, I'll say plus, and if you owe me money, I'll say minus. That's all. I don't really care about how much it is. Okay, what will I get? I may get something like this. So what will the spectrum of this look like? What is the spectrum of a square wave? What is the Fourier transform of a square wave? What will you get? Huh? NF0. Exactly, right? You will get the fundamental and all the harmonics. Okay? No, not that way. It doesn't look like that. But you get something at F0. And in this case, if it is symmetric, you will not get something at 2F0. But in general, you may get that also. You will get at 3F0 and 5F0 and so on. That's all, right? You have a periodic signal. Any periodic signal can be represented like this. Okay? All you get will be impulses at the harmonic frequencies. So that is exactly what will happen here also. So in general, it may not be symmetrical. So you get something at 2F0, 3F0, 4F0, 5F0 and so on. Depending on how you quantize it, after quantization it may not become symmetric. So you will simply get the signal and all the harmonics. That's all. Okay. So this is something we know. That's why I reversed the steps. I first did quantization and then did sampling. Quantization simply makes it some strange looking step like wave, but it is also periodic. If the input is periodic, the output of the quantizer also repeats after one period. But it is not a sine wave, it is non-linear, something. So it will in general have all harmonics. Okay. Is this clear? So quantization simply leads to harmonics, that's all. There will be no noise floor or anything. So simply if the original thing is a sine wave with a frequency f, it will have f, 2f, 3f, up to all frequencies. Now what happens if I sample it? Let's recall the story. We sampled and then quantized. Now for the sake of analysis, I said it is easier to quantize and then sample. So now I have completed half the step. What will happen if I sample this? Okay. So what will, so let's say my Fs is somewhere here. So Fs by 2 will be here. So what will happen? Aliasing. Everything beyond Fs by 2 will alias back to within Fs by 2. Right? So what will happen to this 2F0 tone? Where will it go? You look at how much this is, and it basically comes back this way, right? Okay. And where will this go? Everything beyond Fs will again, it will appear here, right? This will have gone here. Fs will go to 0. Okay. The rule is Fs by 2, Fs. So everything between Fs by 2 and Fs, you flip it around and plot it backwards, right? That's what happens. Is this okay? So Fs by 2 will remain at Fs by 2. Fs will go to 0. And between Fs and 3Fs by 2, you just plot it like this. Let's say you are given the continuous spectrum and you want to see the aliasing. This is what you will do. This is the algorithm. Okay. Essentially you are repeating this, but remember that minus Fs by 2 to 0 is the same as 0 to Fs by 2. So that's why we are just doing the flipping around. Okay. So all I am doing is I will take this segment, put it on top of this, the next segment, put it on top of this, and so on. Okay. So is this clear? So all the high frequency tones will come here. So the next one may come somewhere here and so on. So what will happen? It cannot be reconstructed. Okay, that's okay. But let's see whether it can be reconstructed or not. Because clearly we do it in real life. In fact, as I speak, it's getting recorded here as digital. Hopefully you can listen to it. So that means it can be reconstructed to some extent. But what will the spectrum look like? Now, this is sampled, right? So that means we are only interested in the segment between 0 and Fs by 2. Okay, this much. So what will the spectrum between 0 and Fs by 2 look like? So, alias distortion. So we have F0, the main signal that we always had, and then all the distortion components get folded back into 0 to Fs by 2, right? So you'll have lot of tones, infinite number of tones really. Now depending on the frequencies and the relationship, you may be able to distinguish them as tones. It may smear out as noise. So that is what quantization noise is. It is just alias harmonic distortion. Okay? This is okay? So that's how we get, so that's what I was trying to get at. It is true that it will become noise, but how does it become noise? Why is there noise? This is what happens. You have harmonic distortion which gets aliased, and you have a large number of tones, an infinite number of tones. So they will fill up all the gaps between 0 and Fs by 2 typically. So that will look like noise, and that's what we call quantization noise. Okay? So this is what I described so far. I first do quantization, which means that I am passing it through the nonlinearity on the left side, a step-like nonlinearity. Okay. So if I have this black sine wave, I will get this red step-like wave. We don't really care at this point what it is, except that because the sine wave is periodic, this is also periodic. So what will happen? The original sine wave was at this point. Okay, the red peak, the very first red peak that you see. Okay, and then the quantized stuff will have this harmonics. It will have this second harmonic also, and then third harmonic. Somehow in this case fourth harmonic is missing. That's a coincidence. It doesn't have to happen. And fifth and sixth and so on. Okay, it will have all these harmonics. Okay, And on the x-axis, I also plotted this 1 corresponds to Fs. Okay. So what I have done is, this black stuff here is simply, I have taken 1 to 2, folded it back here, 2 to 3, folded it back here, 3 to 4, folded it back here, all the way to infinity. Okay, I folded everything back to 0 to 1, which is what happens when I sample it, right? The 0 to infinity gets copied, so it becomes 0 to 1. So I will have all these tones, okay, which if you simply look at it, it doesn't look like it has any relationship to the original one, but it's really aliased harmonics, okay. And on the right side, what I've done is to expand the 0 to 1 region, okay. So you have the main signal here, and also 0 to half is the same as half to 1, because it's a real signal. So let's concentrate only on this. And there are a lot of other tones, as you can see, and which look like noise, right? It looks some random variation in strength, it looks like noise, and that is what is known as quantization noise. Okay, so that's the spectral density of quantization noise. And the blue line is sort of the average strength of all of these things. Okay, so you can see it varies a lot around the average, but this is the average, and we'll use that average number later. Okay, so is this clear what the spectrum of the quantization error looks like? So this is very important if you have to simulate or test A to D converters to figure out, to know what the quantization is, what to expect. When you simulate it, if you put in a sine wave, you will see all these other tones, and that is quantization noise, and that's how they come about. Okay. Any questions so far? So again, I have said this now. Now exactly where the tones are depends on the ratio of Fs to Fin. Okay. The reason I say this is, let's say the input tone was at Fs by 4. What will happen then? This quantization noise spectrum is mathematically also a very complicated thing. But we have to make many assumptions before we get this noise-like behavior. It's good to know what all those things are, right? So let's say originally my sine wave was at Fs by 4. Okay. Where will the harmonics be? I quantize this. Where will the harmonics be? At what frequencies will they be? The sine wave is at Fs by 4. Where will the harmonics be? No. I am just quantizing it. Okay. So I am getting that step-like waveform. If I have a sine wave at Fs by 4, the spectrum will look like this. It will have only an impulse. If I have some other periodic wave with a frequency Fs by 4, what components will it have? All integer multiples of Fs by 4. Okay. So in this case, we will have Fs by 4, which will look more or less the same. Then Fs by 2, 3 Fs by 4, Fs, 5 Fs by 4, and so on. Okay. And then I sample it. Okay. What will happen now? How many tones will we have? After sampling, there will be aliasing. Where will all these tones move to? What will happen to the tone at Fs by 4 after sampling? Where will it be? At Fs by 4. Right? There will be no aliasing for this. For Fs by 2? Fs by 2. Same. Fs by 2 will be the same. Fs will become 0, right? What happens to 3fs by 4? Where will it come to? Fs by 4. What will happen to the one at Fs? What will happen to the tone at Fs? It will go to 0. 5 Fs by 4? Fs by 4. Okay. So actually there will be only 3 tones in this case. You will have something at 0, something at Fs by 4, something at Fs by 2. So I am showing this to point out that quantization noise, I said, will give you some noise like spectrum, but it's not always true. You can always pick the ratio of input frequency to the sampling frequency so that it looks something weird like this. There are only 3 tones here. There is no noise. Okay. So this is important for a couple of reasons. First, to understand that the spectrum of the quantization noise will have a lot of variations. And secondly, when you want to analyze the quantization noise, if you put in a sine wave like this, it's not very useful. You will not be able to figure out. Okay, because there will be lots of different kinds of errors in an A to D converter, and you should be able to distinguish between all of them. There will be harmonic distortion, there will be noise, everything. If you get something like this, can you tell if it's harmonic distortion or noise or anything else? No, you can't tell anything from this. So it's also, understanding this is also useful to figure out how to choose the signals to test your A to D converters. Okay, or D to A converters for that matter. Okay. So in general, it can look like noise, but it does not have to look like noise. Okay. So especially if Fs by Fin is some integer ratio where P and Q are small integers, it doesn't look like noise. If P and Q are large integers, you will get a large number of tones and it will look like noise. And if this ratio is irrational, it will actually be quite continuous. Okay. So that will come into picture later. Right. Now, a very crude approximation to all these tones, because to find these tones you need to know exactly the signal, but that's not what you want to do. Okay, you want to say something in general about quantization noise without every time looking at what input signal is being fed to it. Okay, clearly the guys who designed the A to D converter here don't know what I am speaking, but still they guarantee that the quantization error spectrum will be of something in the general case. Okay. And that will be true even when I am speaking. It is true that the quantization error will be something like that. Okay, so that's what we are trying to do here. So many cases we just have represented by this average spectral density and then call it white noise. It's not a very good assumption, but it holds in many cases. Okay. Any questions? So the two bottom line things to remember are quantization noise spectrum is nothing but aliased harmonics. Okay, and this you can very easily see if you reverse the order of sampling and quantization. You first do quantization, you get harmonics, then you do sampling, you get aliasing. And you get aliasing of a lot of tones that looks like quantization noise. Okay, any questions on anything we discussed so far? Yeah. Yes, it will. So generally, yeah, if you increase the number of levels, the harmonics will go down, and also when the alias back, the strength will go down. Okay. This, I mean, you can take the extreme case of almost an infinite number of levels. Then your output looks almost like the sine wave. So even without doing any analysis, you know that the spectrum should look like that of a sine wave. Anything else? Okay. So now we know something about, yeah. Yeah, that's true. Those are all details. What will happen is that will modify the. So when you assume an ideal sampling, you will simply assume repeated stuff. When you have some aperture time, there will be some filtering effect. Okay. So, but it's not a significant thing, at least at this level, right? The effect of aperture time, we have not even come anywhere close to that. And if the aperture time is very small, it is good enough to simply say that the spectrum repeats. Okay. Any other questions? Okay, so I've shown a quantizer here on the left side. The input is called Y and the output is called V. This nomenclature comes because later we want to use it for something else. Now, it will introduce some error. Okay, some error E. Now, the error depends on the inputs, and we can model it as some error being added to the input. Okay, I am not doing any transformation or anything here. I am simply representing the output as the input plus some error. This I can always do. Okay, E is whatever the quantization error is. I don't know what it is. I need to know the signal to find out that thing. But E is whatever the quantization error is. Okay. So this is just a model. This is a very commonly used model because already we saw that simply to get the quantized sine wave spectrum, we had to go through many steps. But so in order to be able to do it, even design an A to D converter, we have to make many approximations. So a start to that is modeling it as an additive error. Okay, there is no approximation here. It's simply a representation. The approximation will come later. Now, what is the distribution of quantization error? I already said, we discussed it, that if you round off your expenses to 1 rupee, your error can be at most plus 50 paise or minus 50 paise. Okay. So similarly, if the input goes from 0 to 7.5 VLSB, that's what I've shown here. When the input is 0, the output is 0. That is from our quantizer characteristics. That's what I've assumed. Okay. So for 0 input, there is no error because the output is also 0. Okay. When the input is half VLSB, just below half VLSB, the output is still 0. Okay. So this is an error of minus half VLSB. Okay. Depends on whether you take output minus input or input minus output. And just above half VLSB, it jumps to 1 VLSB. So it will become plus 1 VLSB error. Okay. So the error goes between minus half VLSB and plus half VLSB, and your VLSB is like your 1 rupee. Okay. So it keeps on going like this. As you increase the input, the quantization error magnitude increases, then it jumps to the other side, then it comes down to 0, then it increases again, jumps to the other side. This is what happens, right? So this is very easy to understand. So the quantization error is always in the range minus half VLSB to plus half VLSB. Now we want to find out what the quantization error is for some arbitrary signal. Like I said, every time you can't sit and calculate the waveform and find the quantization error. Now it turns out that the quantization error will be uniformly distributed between minus half VLSB and plus half VLSB. What I have shown here is the probability density function. I am assuming all of you are familiar with this. Is it okay, or you want to know the definition of this? Probability density function, everyone is comfortable?
You made a statement that this error is now not statistically independent but dependent on the input signal, right?
That's correct.
Then you cannot make uniform distribution because as the signal characteristics change, the error characteristics will also change.
That's correct. So what happens is that if you have a significantly large number of levels in your range, now more or less whatever input signal you put in, you will get uniform error. Okay. So this can be simulated or seen. Right.
The mathematical simplification problem is, but if it is relatively similar, then you cannot make uncorrelated.
No. It can. I didn't say anything about uncorrelated. Right. I never said anything about uncorrelated. I'm only saying it is distributed uniformly. That's all.
So if the signal is related, it may so happen that the signal may not very uniformly.
No, absolutely. See, you can always find a signal for which this is not true. For instance, if I give a DC, the quantization error will be constant for all time, and there is no distribution here. Okay, I am assuming that the signal varies over some range, right?
But some of the cases, the nodal distribution also.
Which one? No. What I am saying is, for most signals, it is likely to be uniform. Okay. So let's say I take this sine wave, right? I have cut it up into all these pieces. So the moment I talk about distribution, I am talking about statistical quantities, right? So if I have a number of different signals, what is the distribution likely to be? Okay, or if the signal itself has some variations like this, which is not a sine wave, but what is the distribution likely to be? So it will get, there will be some values between this and this, and some more values between this and this. Okay. Now if I take a large number of levels, right, what will happen is, what does the distribution mean? How the error is distributed between these two values, or between these two, or between these two, and so on. Okay. Now when the sine wave is rising, maybe the error is, the value is here. Okay. Maybe when it is falling, it's at a different value. Maybe when it is going through different cycles, it's at different values. Okay. So what happens is, when you cut it up into many parts, it will be uniform. Okay. We can go through more mathematical description of it if you like.
The problem is that I'm saying if it is related to the input signal,
Yeah.
I cannot have that as a thing, and why to say uniform?
No, because it will be uniform. No. First of all, that is very difficult to come up with a description of quantization noise for every input signal. Now the second thing is, for most input signals, if you calculate the quantization error, it will be uniform. It's not some assumption I'm pulling out of the hat. Okay. So maybe we can. So first of all, I'm talking about statistical quantities. So let's say the input itself has some distribution. This is the probability density of the input. Okay. The input itself is distributed in some way. I don't know what it is. I don't care what it is. Actually, let's say it's some stuff like this. Okay. Between the negative and maximum and the positive maximum, it is distributed like this. And my quantization levels are here. Okay. And I want to find the error, distribution of the quantization error. How will I do that? I just have to cut up different pieces and add them together. Okay. So from here to here, this part will go to 0 error, or rather I'll take minus half to plus half, so I'll add this. Okay. I'll take the next piece which is here, and to this I will add that part. Okay. And similarly, this piece is here, I'll add that part, and this piece that's here, I'll add that part, and so on. So when you add up many pieces like that, regardless of the original shape, it will turn out to be uniform. Okay, here already you can see one part is going down, other part is going up, this part is going down, this part is going up. If you add up all of them, it will look like a uniform error. Okay, so the original signal distribution is not all that important. What is important is it is cut up into very small number of pieces. Okay, another way to think about it is, let's say I cut it up into a really small piece. Now each piece is constant, and when you add up all of them, it will become constant. Okay. No. No, how are you saying that it is insignificant? No, it is certainly not implying that. I am only saying that. Yeah, that's right. That distribution is uniform. It is equally likely to be. So let's say LSB is 2 millivolts. So this is minus 1 millivolt. This is plus 1 millivolt. All I am saying is I am not saying it will be at minus 1 millivolt. I am saying you are equally likely to find it between minus 1 and minus 0.9 millivolts. The likelihood of finding it here and between plus 0.9 and 1 millivolt, all these ranges are the same. That's what uniform distribution means. It doesn't mean it's a constant, right? Yeah. So all it is saying is if the likelihood of finding it, so let's say your steps are here and you have some sort of random like signal. Okay, the likelihood of finding it here is the same as finding it here, is the same as finding it here, is the same as finding it here. I'm never saying that it is only at one point. Okay, that's all. So this is actually a very good assumption. You can simulate it also and see very easily. You put in even a sine wave and you find the distribution of the quantization error, it will look more or less uniform. Okay. The only time it will not be uniform is if you divide it up into only 2 steps. Okay, then it will become very crude. But as long as you have a reasonable number of steps, it doesn't have to be very large also. This is a very good assumption. Okay. Is that okay? Okay. So it will be uniform, and so that is represented by the probability density function. So everyone is familiar with the use of the probability density function. It only says that if you want to find the likelihood of error in some range, you integrate this density function in that range, that will give you the probability. Now obviously, it will be there somewhere. So the probability of finding it somewhere is 1. So the area under this is 1. Okay. Now because this is constant and the area is 1, you can find out how much this height is. Okay. The height is simply, what is the height? 1 by VLSI. Okay. Errors in? No, that should not happen. That will not happen, right? If you are rounding off to 1 rupee correctly, see, I am assuming so far that you are doing your operations correctly. If I give you 50% and you round it off to 2 rupees, then there is something wrong in the operation. You have to round it off correctly. Once you do that, you will have only half LSB error. Okay. Type meaning? Yeah, surely. You can find that. Okay. So that will come to later, what other errors you will make. So far I am talking about the errors inherent in quantization. It's not a mistake I am making. Okay. If I build an A to D and I make some mistake in a design, I can get other errors. Okay. But this is not a mistake. The moment you quantize, the moment I say rounding off, I will be making errors. That's the thing I am talking about. It's inherent. Similarly with sampling, I get these copies of the spectrum, and that's not because of some mistake I made. The process of sampling means you will get those copies. Similarly, the process of quantization means you will get this type of errors. Okay. So the word error should be used carefully here. It's inherent to the process. Okay. Now beyond this, because I don't know how to design it today, I could be making so many other errors. That we'll see later. Okay. Now if we have a height of 1 over VLSB and a uniform distribution like this, it's a well-known thing that the mean square value of this is VLSB square by 12. So this, as a result, probably many of you are familiar with. Okay, but this is how the whole thing comes about. Because it is a uniform distribution, and you find the mean square value of this. If you want, we can also calculate it later and see. But for now, please take it that the mean square value of error is VLSB square by 12. So mean square value is something like mean square value of a sine wave. Right? You want to see how much the energy is. Right? You want to represent, because now it is uniformly distributed, at every instant you can't say what it is. But you want to give some measure of size to this signal. And that size, like for instance, you use root mean square value for a sine wave, you can use the root mean square value for a random signal. And that is VLSB by square root of 12. Or the mean square value is VLSB square by 12. Okay. So that's a measure of how large the error is. Is it okay? How many of you have calculated you know how to calculate the mean square value from the distribution? You know this, or you want me to do this? Let me proceed a little further. I'll come back and do this. So mean square value of distribution is very easy to calculate, but it's like a measure of the strength of this error, okay, which is what we want to find out, right? You will have an error, and now every instant you can't say the error is 1 millivolt or something, but statistically you want to give some measure to the size of the error, and that measure is this mean square error or root mean square. You can take the square root of this and you get root mean square, okay. Okay, this is fine. The distribution of the error, because this is a statistical quantity, there are different things. There is the distribution which says how it is distributed over the range of possible values, minus VLSB by 2 to plus VLSB by 2. Then we will also be talking about spectral density, which says how it is distributed over the frequency. Okay, so that is a completely different thing from this. Right? We will look at that also. Now, like I have been saying before, if you know the input signal, you know the quantized signal, you know the quantization error also. So it is fully correlated to the input signal. Okay, is this part clear? It's not independent of the input signal at all. It is completely dependent on the input signal. If I give you the input signal, you can certainly find out what the quantization error is, right? Now the whole point is we don't want to look at the input signal in every case, because when you are designing you want to take some sample signal, do your simulations, and finally guarantee that it will meet some performance. Okay. Now if you look at the properties of the quantization error, I already showed you that it is uniformly distributed and the mean square value is VLSB square by 12. Sorry. Mean square value is VLSB square by 12. Now, and the average value is 0. Okay. The average value of 0 also comes about simply from this. It's equally likely to be negative or positive. So the average, on the average it is 0. Okay. I mean, this is exactly like you may be rounding up or rounding down. When you are calculating accounts for a number of items, in some cases you rounded up, some cases you rounded down. On average it is 0. That's why you are comfortable doing this also, right? So mean is 0 and the variance is VLSB square by 12. Now these properties are independent of the signal for most signals. Okay. So the exact quantization error is dependent on the signal, but you take some reasonably complicated signal, you will either get, you will always get 0 mean and variance of VLSB square by 12. Okay. And the statistics are independent of the input signal. Okay. So it is, that's why these things are of interest, right? It is more of interest because independently of what the signal is, we get this variance and this mean. Okay. Now, it also turns out it can be somewhat approximated by a white spectral density. What is a white spectral density? What does white spectral density mean?
White spectral is all components like white light.
White noise. So it means that if you look at the frequency content of the signal, it is the same at all frequencies. Okay. So I take the input signal. The input signal has some frequencies, and after sampling it will have frequencies from 0 to fs by 2. What this white noise assumption is saying is it is equally distributed between 0 and fs by 2. Okay. Now, yeah. Now this is how it is distributed. You have all these tones in reality. Okay. For the sake of convenience, I will assume that it is equally distributed between 0 and fs by 2. Now this assumption is not as valid as the previous one. The uniform distribution over amplitude is very true, okay, for most signals. But this white noise is not a very good assumption, but without it we can't do any calculations at all. So we go ahead and make this assumption. Okay. Is this clear? The two are completely different. This says how it is distributed over amplitudes. This says how it is distributed over frequencies. Okay. So it is distributed uniformly over frequencies. This is an assumption. And because of this, we can think of quantization error as some kind of white noise. Okay. Now what I have shown here is the spectral density with respect to f. in hertz. Okay. Similarly, when you do calculations with discrete time, you don't use hertz, but you use this normalized frequency 0 to half. Okay, all frequencies are normalized to fs. So then also it will be uniform. The constants will change. That's all. Okay. The important thing is the area of this is VLSI square by 12, because the area under the spectral density is nothing but the mean square value. Okay. Hopefully you are somewhat comfortable with the spectral density and mean square value, then you will be able to figure this out. Okay. Any questions on this? Firstly, you quantize it, you are likely to find it between, equally likely to find it anywhere between minus half VLSI and plus half VLSI. In addition to that, you want to find the frequency content of this quantization error. And that, the frequency content is harder to determine, but it's a somewhat reasonable assumption to assume it to be a constant. Okay? Is it okay? Now, one key thing to remember is that the variance is VLSI square by 12. Our RMS value is VLSI by square root of 12. So, finally we come to how much the error is. Okay, this is what we wanted to find out. We want to sample and quantize because we want to have a record with finite number of points which we can store and process and so on. Now, sampling gives you some kind of errors, quantization gives you some other kind of errors. Now, we want to describe it by some number, okay, to say that it is good. We already said that the quantization error can be modeled by some white noise like thing in many cases, in most cases. Okay. Now, how will you describe a signal with noise? By the signal to noise ratio, right? When you have some signal and noise, you describe it by the signal to noise ratio. And if the signal to noise ratio is above something, you can identify the signal, otherwise you can't identify. That's how you usually do it. For instance, if some noise is added to this, if the noise level is above some value, you won't be able to find out what I'm speaking. Similarly, this quantization error is described as noise, and here I'll calculate the signal to quantization noise ratio or quantization error ratio. Okay. So let's say I have some sine wave. Now again, a sine wave is the usual representative signal. Actually, I am not speaking a sine wave into this, but that's what I use. And the sine wave extends from minus Vref by 2 to plus Vref by 2. Okay. What is the RMS value of this sine wave? What is the RMS value? Huh? Vref by 2 root 2. So the peak value is Vref by 2. That divided by root 2 is the RMS value. So the mean square value, what is it? Simply the square of this thing, right? That is Vref square by 8. Okay, I just squared it, that's all. Now, I have, let's say I have 2 raised to n quantization levels between the two. Why it's a power of 2 we'll see later. It's a convenient number to realize. That's why most of the time you realize a number of levels which is an integer power of 2. So let's say I have 2 to the n levels. Okay. What is the quantization step? Over the entire range, I have 2 to the n levels. My range is from minus Vref by 2 to plus Vref by 2. And for the signal, I have fit the largest sine wave that I can fit into this range. Okay. So if I do that, its RMS value is this much. Okay. Amplitude is Vref by 2. Now I will also quantize it, and I will quantize it into 2 to the n levels. What is the size of each level? Vref by 2 to the n. Okay. VLSB is Vref by 2 to the n. What is the mean square value of the quantization error? What's that? VLSB by 2 square. Why? We just calculated the RMS mean square value, right? What is the mean square value? Vref square by 2. Why? VLSB square by 12. Right? So, the mean square value of the noise, this is for the signal. For the quantization error or the quantization noise, it is mean square value is VLSB square by 12. And how much is it? It is Vref square by 2 raised to 2n times 12. Okay, I have simply squared this and divided it by 12. So, what is the ratio of the mean square values of the signal to noise? So, I want to calculate the ratio of signal strength to the noise strength. The signal strength is given by its mean square value, which is Vref square by 8. The noise strength is given by its mean square value, which is Vref square by 2 to the 2n times 12, or VLSB square by 12. What is the ratio? Pardon? 2 raised to n minus 1. Why? So, I calculate Vref square by 8 by Vref square by 2 to the 2n times 12. I get 12 by 8 times 2 to the 2n. Okay? Or 4 to the n. It's the same thing. And 12 by 8 is nothing but 3 by 2. Okay? So, if I divide a given range into 2 to the n levels and apply the maximum possible sine wave to it and see the signal to noise ratio, signal to quantization error ratio, that number will be this much. Okay? Are you guys familiar with this result? Okay? So, this is the signal to quantization noise ratio. It is 3 by 2, 2 to the 2n, and this has been calculated with 2 to the n levels in minus Vref by 2 to plus Vref by 2. Basically, the range is divided into 2 to the n levels, and also you fit the maximum sine wave to it. Okay? And this is typically represented in dB. Okay? So, you take 10 log to base 10. What will be that number? So, this simply gives you 6.02 n, right? And what is this? 1.78 dB. Okay? So, this is the SQNR in dB, and are you familiar with this formula? Very much, I think. So, this is how you derive it. It's basically the ratio of signal strength to noise strength when the signal range is divided into 2 to the n levels. Okay? This is only for a sine wave that is fed to the maximum amplitude. Okay, that's all. So, if you have different type of signals, the mean square value of the signal will be different. The noise will be the same, the signal will be different, and you may get a different answer. But you have to do some test with some representative signals, and sine wave is usually what is chosen. Even when you want to measure an amplifier, you feed in a sine wave and specify. If you take the data sheet, it will tell you what happens to a sine wave. Similarly, you can give you design an A to D, say what happens to a sine wave when it passes through it, and after that, if they want to figure out for other signals, they can do it themselves. Okay. The very least, you can calculate the quantization noise from this, right? Okay. Is this clear how the formula comes about? So this is all about sampling and quantization process. This is a very commonly used formula. Okay. So I just, we can take, I think it's time for the break. Yeah. I'll just go through a couple of more slides summarizing this thing and we'll break. Okay. I hope everyone is clear with this because this sets the foundation for the signals in an A to D, and then Shanthi will take over and do the flash. So to summarize, I have a continuous time signal. I sample it, it will repeat, and I quantize it. I will get some quantization noise, which is given in red. It's assumed to be also uniform with frequency, and the height is VLSI square by 6fs. When I plot it with respect to the real frequency in hertz. Okay. Now when I reconstruct it, remember when I had sampling only, I reconstruct it, I get back exactly the original signal. When I have sampling and quantization, I reconstruct it with this filter, I will get signal plus some noise like thing. Okay. So the quantization irreparably damages the signal. You will get some noise. And we already know how to calculate the strength of that noise. The mean square value is VLSI square by 12. Okay. Basically the area under this part. Okay. So what is analog to digital conversion? It has an analog input V in and a digital input D out. Okay. It only says which range your signal is in. Huh? Bandwidth? No, it should not change at all. It should be simply a copy of the signal. Right? It will be the same. What will happen is, you will get this black part which is the signal and this red part which is the error. When you take more levels, this red part will go down. Okay, the black part is your original signal, that will remain the same. Okay, whatever the junk that you add to it will keep on changing depending on the number of levels you have. Is that okay? Not okay? No, what I am saying is, this black stuff is the signal that you have, and the red stuff is the quantization error that is added by the quantizer. Now, as you change the number of levels in the quantizer, you keep the same input signal, that means the output signal part will be the same. As you change the number of levels, this red part may go down or go up. If you increase the number of levels, it will go down, because the quantization, you are basically rounding it off more finely, the quantization error will go down. If you reduce the number of quantization levels, this red part will go up. Okay, you will get this black plus red, and the amount of red is dependent on the number of levels. You will have lower density. That's actually absolutely true. What will happen is, the area under this should remain the same. Okay, the area under this part. The density will, because the area has to be the same. If you increase Fs, this will come down. What is that? Yeah, you can talk about it. So it is true. If you increase Fs and keep the number of levels the same, the density will come down. But you are integrating over a larger area. But actually this very fact is used when you do oversampling converters. Okay. When you do oversampling converter, here I said that your Fs to be at least 2 times Fb. Okay. Once it is 2 times Fb, you can reconstruct your signal. So from this point, from here, it doesn't look like there is any motivation to make it, let's say, 20 times Fb. But the point of making it 20 times Fb would be exactly what you said, that this red line will come down because the density will come down. Then you can have a greater signal to noise ratio. Okay, so that point is used in oversampling converters, but that will come to hopefully later. Okay. Anything else? So So we have the input, you will get the digital output, and there are two other sort of parameters of the A to D. One is Fs, the sampling rate, which you have to adjust based on the input signal bandwidth. The other is Vref. Okay, that is the signal range. The final thing that you have to specify is the number of bits, because we always take the number of levels to be some 2 to the n, where n is the number of bits. Okay, so Vref will be cut up into 2 to the n levels. That will give you VLSI, and you have the sampling rate and so on. Okay, so this represents the A to D process, and this is the characteristic of the A to D. So we can come back after the break and continue. Okay.